M0NTV, and welcome back to my shack and to another video. And this one is about something that I really struggled with when I first started on this whole journey of trying to build my own radios. And that is, I was looking at designs that called for wideband RF impedance matching transformers. And I didn't really understand how these things worked, and I wasn't at all convinced that I was building them right. And so I am by no means an expert. All I am is a bloke that's built quite a few of these things, and I just want to understand them better so that I can build better transformers. And I offer this video to you in that same spirit. So I hope that you find something that's helpful and something that is interesting. And as always, I hope you enjoy. So let's have a look at building some transformers for wideband RF impedance matching. And the challenge we are trying to meet is pretty simple, really. It's how do we connect a signal source to a load? And you might think, well, why don't you just connect the source to the load? And you absolutely can do that sometimes. You can do that when the source impedance matches the load impedance. But what if the source impedance doesn't match the load? So let's say we had a 200 ohm source going into a 50 ohm load. Well, essentially, as I'm sure you're aware, the signal which leaves the source expects to see 200 ohms. When it meets the 50 ohm load, only a certain proportion of that signal, and in this case 60%, will actually be absorbed by the load, and 40% of that signal will be reflected back to the source. Now, it's not the end of the world, and there's a lot of urban mythology on the internet about SWR and reflected signal. The truth is, reflected signal in and of itself is not lost signal. All that happens is that when it gets to the source, it gets reflected back and joins the other part of the signal going from the source. So it will just bounce back, as it were. The problem comes when you consider your feed line. The issue is, with any connection, there will be a certain amount of loss. And if, for instance, you had a lot of loss on your connection, the trouble with constantly reflecting your signal back and forth many times is that every time it goes through the connection, it experiences loss. So that will be lost signal. It's just heating up the wire. So the more signal you can get to be absorbed into the load on the first hit, as it were, the better. So that's why we try and match impedances, because it means less reflected signal. And why this is important to us is because, unlike at audio levels, lower frequencies, where you're not bothered about matching impedances. As a matter of fact, you don't want to match impedance. You would want to have an output impedance that was going into an input impedance of the next stage at least 10 times higher. And we do that to maximize the voltage gains. But actually, at RF level, most of the time, we're not that fussed about precisely how much voltage we've got and how much current we've got. What we're interested in is preserving the power levels going through. So the voltage and the current will kind of go up and go down. That's fine as long as the power can be maintained. And maximum power transfer occurs when impedances are matched. So that is why we have to try and do this. Now, there are different ways you can do it. I've done at least a couple of videos about LC matching networks, and that's a very effective way that you can match impedances. But it tends to be of a more restricted bandwidth. You get a very good match, but not over a very wide bandwidth. What I'm concerned with looking at today is how we match wide band impedance mismatches. So say over the whole of the HF band, that's what I'm looking at. And so we can build a transformer. The simplest kind of transformer that we can build is something called an Autotransformer, and the auto comes from the Greek, just means self. And the reason it's called that is because it's just one winding. It's not like a conventional transformer where you have two windings. There's just one winding and a tap. So you tap off that winding. And I'm not going to spend too much time on this. I have built one and I've tested it, and you'll see that a little bit later. But just for completeness sake, I thought I should mention it. But essentially all an Autotransformer is a tapped inductor. And it probably reminds you, when you look at that schematic here, of perhaps a potentiometer. And in many ways, it functions like a traditional voltage divider. Only instead of having fixed resistances that voltage is dropped over, what we have is voltage being dropped over inductive reactance. And it has a similar effect, and depending on where you tap it, and you can have many taps on an Autotransformer, you can match different values of load. So that's an Autotransformer. That's about as much as I'm going to say about an Autotransformer, other than showing you the one I built, because I want to spend most time looking at what we'd call the conventional transformer. So the conventional transformer looks like this, at least in its schematic form. So it's essentially a core. I am going to be using, as you'll see, ferrite, toroid and FT3743. And how it works at the most basic level is when you put an electric current through a wire, any wire, it will generate a magnetic field. And I mean, this goes back to the beginnings of electronics and the nature of the universe, really, doesn't it? I mean, electromagnetism, that's where it's all built upon. So a current passes through a wire, it generates a magnetic field. Now, if you were to coil that wire up, that would intensify the strength of the magnetic field. If you were to go the next step and take a core that has a high permeability, something like a ferrite core, and wind those same turns through that, that will massively increase the strength of the magnetic field. Now, where it gets interesting is, let's say on our core where we've got our winding, and we call these incidentally the primary and the secondary windings. The primary winding is simply the winding that is attached to the source. The secondary winding is the winding which goes to the load circuit. So let's say we've got our primary on, we put our secondary on, something interesting happens. Because if we've got our electric current going through our coil of wire on our ferrite toroid, generating this pretty strong magnetic field, if there's another wire very close to it, which is part of a circuit, needs to be part of a circuit for this to work, then what happens is there is a transfer of energy, of magnetic flux. And energy here, magnetic energy, so the electric current generates this magnetic field, but it returns the favour in this other winding. So it kind of happens in reverse. So that the energy that's stored in the magnetic field here induces in this winding, the secondary winding, an opposite flow of electric current, which is why I've got the arrow pointing up. Now these little dots are phasing dots, and so this dots they'll tell you what's the top and the bottom of the winding, which is useful when you're actually winding these things. But really, this is just to say this is where you measure the current. So the current flows in through this dot on this winding and out through this dot on this winding. If you had the same number of windings on both of these turns, if you had a 1-to-1 transformer, then you would find an equal and opposite flow of electric current. If you had a different number of turns, then actually what you're doing is rejigging the balance, the ratio between the voltage and the current in your signal, which will mean, of course, a different impedance. So this is how we accomplish this impedance matching, by varying the number of turns here and here. Whatever the source is here, even if it's a different impedance to the load, by a bit of jiggery pokery here and the number of turns that we have, it'll be happy and thinks it's seeing its own characteristic impedance. Clever stuff. Now, this is great, and we call this an ideal transformer, and if you're ever going to model one of these in LT Spice or something like that, you can do that. You can put this in and it'll work like a charm. The truth is, though, that you'll never build an ideal transformer, because in the real world you can only ever build a real transformer. And take a good look at this, because the next picture is going to look very different. What you're actually building when you build one of these electrically actually looks far more like this. Wow, we're not in Kansas anymore, are we? Now, just to get your bearings, here's your actual original transformer. That's not changed, the two windings on the toroid there. Here's your source. And here's your load. But my goodness, there's an awful lot of other things going on here as well. Now, I'm going to explain just basically what's going on here, because in a few moments, when you see the real transformers that I built and the testing that I do, we will see some trends. And in all truth, I've been building these transformers for a few years now, and by and large, I haven't really been bowled over by their wideband impedance matching capabilities. I model something in LT Spice, I'd expect it to work really well, and it worked, but not as well as I'd hoped. So I'm going to show you this stuff, because when it gets to seeing the results, I think when you can understand some of what we're dealing with here, it will help you to, first of all, interpret those results and understand what you're seeing, but also some of the things I'm going to tell you about here we can do very little about, some we can do something about. And I present this in order that we might all be able to build better transformers. So here we go. So I've labelled these different elements here. So you can see red resistance, green inductance, and blue capacitance. So R1 and R2, first of all, that's here and here. These represent the resistance of the primary and the secondary winding. What is a transformer? It's two inductors wound together on a core. What's an inductor? It's a bunch of wire, right? And wire will have resistance. It doesn't matter how good it is, even if it's the most fine grade copper wire, there will be some resistance. You can't do anything about that, because you've got to use wire if you're going to build a transformer. So there will be a certain amount of resistance just in the physical properties of the wire that we're using to build the transformer. RC is this resistance represented here, which manifests itself as a resistor, a shunt resistor to ground. This is the core loss, and those two words hide a multitude of complexity. There are three contributions to this, really: eddy current loss, hysteresis loss, residual loss. I'm not going to go into those at all, you'll be relieved to know, but just to say what's happening when we inject an RF signal into our transformer. It's like the RF signal causes vibrations in the magnetic field of the core material itself. And this movement, this vibration, causes a loss of energy. And a matter of fact, the higher the frequency of the RF signal, the faster the vibration and the more energy is lost. So you can see where we're going with this. What this means, of course, is that this will actually compromise the high frequency response to our RF signal. So it's not going to work as well at higher frequencies because the losses are greater at higher frequencies. So that's the core loss, and that kind of works alongside the one next to it, LP, which is the magnetizing inductance. Now this does the other thing. The RC kind of compromises the high frequency response. The LP, the magnetizing inductance, actually that compromises the low frequency response, as you might expect if you have an inductor shunted to ground. What is this? It's the permeability of the core itself that you're using. It's the cross-sectional area of the core with what it physically looks like. It's the number of turns you put on it. And essentially what it does is means that the transformer doesn't work as well at its lowest frequencies. And all of this means that it's important to try and get the right kind of core that will work within the frequency range that you want. But even within the range you want, there's no such thing as a free lunch, because you've got these things which are kind of part of the core itself. I mean, all right, you can decide how many turns you put on it, but the rest of it is really the core material. But we're going to go and move on now to some things that we can have more influence over, which is L1 and L2. Now, this is the primary and secondary leakage inductance. Now, depending on how you wind your two windings on your core, depending on how close together those windings are, you will get a tighter or a looser coupling between those two windings. And if you have a looser coupling, if there's more distance between these two windings, then what that means is that not all of the inductance of your windings get used in this transfer of energy from one winding to the next. There's a kind of bit of the inductor that gets left out, if you like, that doesn't take part in this magnetic flux transfer. And that manifests itself as a series inductor. Well, now we're really in trouble, aren't we? Because if we've got a series inductor in the signal chain, clearly that's not going to be good for high frequencies. But we can do something about that, of course, depending on how we wind the two windings together. We'll come back to that. But then we've got the capacitance. And there are two types of capacitance, and I'll put the other one up here as well so you can see them both together. So you've first of all got C1 and C2, and these appear like a shunt capacitor across the source and across the load. And this is what we call the intra-winding capacitance. Just imagine for a moment one winding. Forget the other one, but just pretend we've got one winding on the core. All those little turns of wire, particularly if they're close to each other, will exhibit a capacitance. And we call that intra, in between, winding capacitance. But we also have to contend with C3 and C4. And you can see these link the two sides of the transformer. And this is what we call the interwinding capacitance. In other words, this is the capacitance that exists between turns of the different wires, of the different windings. There's capacitance there as well. And that manifests itself as shunt capacitance. So, if we've got this series inductance and shunt capacitance, that is a low pass filter. So, that's always going to compromise our high frequency response. So you can see there's a lot of stuff going on here. Some of these things we can deal with. These are interesting because this leakage inductance and the winding capacitance, if you reduce the leakage inductance, you can only really do so by increasing the winding capacitance and vice versa. So it's a bit of a juggling act, but it can be done. And being aware of these things will help us when we actually come to build the thing ourselves. So what are we going to build? Well, here is the test transformer that I'm going to build. Essentially, we're thinking about a 200 ohm source and a 50 ohm load. And the reason I'm doing that is because that is a very familiar challenge that faces homebrewers, particularly if you've got a common emitter amplifier where the collector circuit wants to see 200 ohms or so. But you want to feed the output of that amplifier into the next stage of your radio that wants to see 50 ohms. So it's a useful thing. Now, what you can do is to test this in many ways. I'm just going to show you one way of testing this. And to make life easy for ourselves, we're going to swap these over. These transformers are by and large bidirectional. That is to say, we've got a 200 ohm source and a 50 ohm load, but we could swap those around and have a 50 ohm source and a 200 ohm load. And that will make life easier for us when we test it. And I'm going to put 10 turns on my primary winding and 20 turns on my secondary winding. How do I get those values? Good question. Well, first of all, we need to consider what the impedance match ratio is. And all you do is you just divide the higher one by the lower one. So if we've got 200 ohms, we've got to match it to 50 ohms. 200 divided by 50 is 4. So that's the Z match ratio, 4. The turns ratio is just the square root of that, and the square root of 4, of course, is 2. Now, interestingly, the turns ratio is also the voltage ratio. It essentially means because we are going from 10 turns to 20 turns, the voltage that we see here will be twice the voltage here because we've increased it by a factor of 2 because the load is much higher. And we've got 20 turns here and 10 turns here. So the turns ratio is the voltage ratio. So you've got twice as much voltage here on the secondary as you have on the primary. And what that means, of course, because we're going into a much higher load, so there's more impedance to impede the current flow, as you probably guessed, you increase the voltage by a factor of 2, but you decrease the current by a factor of 2. So in other words, you get twice the voltage and half the current, which of course means the power is exactly the same, which is exactly what we want to achieve. Well, that's fine, but how did I decide on 10 turns and 20 turns? Okay, let me just briefly show you that bit. Now, there are all kinds of formula that you can use to calculate this by hand if you wish. I'm just going to do some shortcuts here and use one of my favourite websites, toroids.info. I know, I really should get out more. But be that as it may, it's incredibly useful, this site. So first of all, you plug in the toroid you're using. So in our case, it's an FD3743. And we need to ask ourselves some questions. So we know we want to transform 200 ohms to 50 ohms, or 50 ohms to 200 ohms. So we ask the question, what is the lowest impedance that we're working with? Well, 50 ohms. And then we ask, what is the lowest frequency that we're working at? And in my case, that's going to be 1 megahertz, because I want this wideband impedance match to cover the whole of the HF band. So 50 ohms, 1 megahertz, that's the lowest amount of impedance in our transformer and the lowest frequency that we want to use it at. Now, the rule of thumb is that the inductive reactance of the lowest impedance winding needs to be at least 4 times the value of that impedance. So let me put that another way. That 50 ohms that we're trying to match to 200, the winding attached to the 50 ohms needs to exhibit at least 4 times that amount of inductive reactance. So in other words, we need an inductive reactance of at least 200 ohms for this thing to work right. So, and it's very easy with this because you just plug it in. So now my ridiculously oversized cursor here. So 1 megahertz and ohms, 200 ohms. Calculate. And you'll see here, that means we need 31.83 microhenries, 9.5 turns. Now, obviously, you can't have 0.5 of a turn on a toroid. You have to have whole numbers. But remember, this is a minimum. That's great. We can just make it 10 turns. So let's do that. Clear it. 1 megahertz. 10 turns. Calculate. So at 1 megahertz, 35 microhenries, 219.9, so 220 ohms of inductive reactance. So that will do us nicely. So that means we know that the 50 ohms end has got to have 10 windings, and we know what the turns ratio is. It's 2, which means the other side has got to have twice that. So the 200 ohms side has got to have the 20 windings. So that's where we get the 10 turns to 20 turns ratio from. Now, 3 extra things very quickly. First of all, the eagle-eyed amongst you will have perhaps noticed under the application frequency range that for wideband transformers the bottom end is 5 megahertz. So by trying to use it at 1, we're actually going beyond the recommended range. It'll work as you will see, but just bear that in mind. You could use, if you were centering your operations on the lower end, a different core, of course, and you can have a look there. There's lots of different permutations, but it should work fine for our purposes. Secondly, if you are finding that you can't physically wind all these windings on the core that you've got, because this toroids.info will just spit out how many turns you need, it won't actually consider whether it's physically possible to put that many turns on that particular core. So if you run out of space, you can either choose a different core with a higher permeability, so you don't need as many turns, or the easiest thing is just to use the same type of core, a type 43, but just move up. So move up to say a 5043, and you won't need as many turns. And if you keep the same lighter gauge wire, you'll be able to get more turns on there anyway. So that's very useful to know. And thirdly, just bear in mind, these transformers that I'm going to be building are for small signal use. Please don't try and pump watts of power through these. If you want to build transformers for higher power, then certainly you will need much larger cores, and maybe even multiple cores, because that will give you greater power handling capability. You will also need much heavier gauge wire as well that will take the higher current. And the problem is you don't want to put too much power through cores, because you will saturate them, and then the transformer won't work properly. So just consider that if you're going to put a bit more juice through them.
Now, I have covered how to wind inductors before, so I'm just going to very briefly go over it again now. So I've got a little bit of wire, just a tiny bit of wire here, just for illustrative purposes, and I've got my FT3743 core. The thing you need to remember is every time the wire passes through the center of the core, that constitutes one turn. And it's kind of hard to show you just one turn on its own, because it obviously doesn't stay still. So let me just put another one on, and that will anchor it down a bit more. So now pull it nice and tight. That's what you want. You do not want turns, loose turns, flapping around over the core. They need to be making as much contact with the surface area of the core as possible. So if I move my finger out of the way, you might see that a bit better. I'm not sure if you can. So that's 2 turns. Hopefully you can see that there, where we come in, go round, up, round, and then back out down here. So I'm just going to very quickly just stick a few turns on here. As you're winding, just be careful as you're looping the wire through. Just be careful you're not looping it through one of the turns you've already put on. Right, that's a very easy thing to do, particularly when you've got a lot of turns to put on the coil, and that can cause you all kinds of problems. So just be careful. Take your time when you're doing it, and I find it's easier just to keep moving them up a little bit with my thumbnail. You can spread them out in a minute, but just to try and keep them a bit even. So now, I think that'll do for our purposes. When you've completed your windings, what you don't really want is something that looks a bit like that, right? With all the turns up in one bit, and then great big bits of the core with nothing on. We'll see the effects of some of this in a moment. But really what we need to do is to spread those windings out evenly across the surface area of your toroid, but not to fill the whole thing. So try and get them evenly spaced. I'm just fiddling around. I'll show you what I've done in a moment. But try and leave a little gap then at the bottom. So now that little gap at the bottom is brilliant, because what that means is you've got a bit of isolation between the in and the out. It also means that your windings are spaced out, so that cuts down on that intra-winding capacitance I talked about. And very practically, it means you've got a bit with nothing on, which will sit flat and not cause any problems on your board when you solder it down. So that's a very useful kind of thing. So that's what you want to be aiming for. When it comes to putting the second winding on, well, we'll have a look, because we're going to try some experimentation in different ways of doing that. And the last thing I need to tell you about before we actually build and test some transformers is how we're going to do that. So I built this little test jig here. Now, don't worry about this BNC connector because we're not going to be using that, but that was for doing some other kinds of tests with my oscilloscope and testing the voltage levels. But we're not going to do that now. And you remember I said that it would be easy for us if we swapped our load and source around. And so now what we're going for is a 50 ohm source input going to a 200 ohm load output. So this is a 200 ohm resistor, and it is almost exactly 200 ohms. And so what we're going to do is, as I build these transformers, I'm going to pop them in here, and the primary winding, the 50 ohm end, the hot end, the top lead, if you like, of the primary will go to here on the SMA connector, and then the bottom end will go to ground. And then on the secondary winding, on the 200 ohms end, the top end, the hot end, will go to this pad here, which will then go to the load, and then the bottom of the secondary winding will just be soldered to ground. And so I thought if I got the same bit here, that's going to make it easier. Also to say, I'm using exactly the same toroid, the FT3743, and exactly the same bits of wire, right? So it's all the same because I want to try and keep everything as similar as possible to show you the difference that it can make how you wind these things. And the reason why I wanted an SMA there is because of how we are actually going to do the measurement. And the way we are going to measure the performance of our transformers is with a nanoVNA. So this is the latest one that I've got. They are superb little devices. So all we're going to do is, first of all, I have set a sweep on the nanoVNA between 1 and 50 megahertz, and we're going to do an S11 sweep. So in other words, we're sending out a signal on port 1, and then we're measuring how much of that signal is reflected back to port 1. So this will enable the nanoVNA to calculate the SWR, the impedance, return loss, and everything else. So this will be really interesting because it will tell us how well our transformer is doing, because the nanoVNA will be expecting to see 50 ohms. But we know we haven't got 50 ohms, we've got 200 ohms. So this will really be a good indicator of how well our transformer is performing that task of making our 200 ohms appear to the nanoVNA look like 50 ohms. Obviously, you need to calibrate it for the sweep that you're using, and I've done all that. Now, to make life easier for you to see the results, I'm not going to just try and video the screen because that's not very helpful. I'm going to use the nanoVNA Saver software running on one of my Macs, and I'm going to do a screen grab of the results of that, so you'll be able to see much more clearly and compare how these different transformers perform. And so here is my auto transformer. I have wound 20 turns on the one and only winding, but if I turn it around here, you'll see I've got a tap there, and that tap is at 10 turns. So it's 20 turns tapped halfway through at 10. And what you do is you put the end here to the largest impedance or resistance. So that's connected to the 200 ohms there, and then that goes, the other end goes to ground. And then what I'm doing then is I'm tapping off there, and this will be the 50 ohm end, the smaller impedance, and that's going on here connected to the tap. So let's have a look now and do some tests and see how it performs. And so here is the screenshot from the nanoVNA Saver.
And just to familiarise yourself with it, essentially there's four things here. We've got the Smith chart over here. This is just the R, the yellow is the resistive part of the impedance, and the purple trace is the reactive part. Then we've got the SWR down here and the parallel impedance over here. Now, when you're comparing these graphs from one test to another, just be careful and be aware that the scales will be different, because the software rescales the graphs depending on the data for that particular trace. So you can't just stack them alongside each other. But you will see here instantly that at low frequencies, I mean, up to 40 meters, you're probably about 1.5 to 1 SWR, which is absolutely great. But the high frequency performance drops off then. By the time you get to 20 meters and above, it's dropping off. And by the time you get to the top of the 10 meter band, you're up to 3.5 to 1 SWR. So not great. Get away with it for the lower bands, but not so great for the higher bands. And this is what I was talking about, this business of there's a lot working against us in terms of the higher frequency performance and trying to get this line a lot flatter than that. Oh, just to point out as well, I've got here on the S chart a circle of constant SWR set at 1.25 to 1, which would be excellent, and it's there here, and you can see we only have a tiny little bit that actually dips below that line. So that's the Autotransformer. It works after a fashion for the lower frequencies, but not so good for the higher frequencies.
What I've done now is I've wound the same ratio, so 20 turns here in the red and 10 turns here in the kind of bluey green colour. But as you'll see, I've wound them completely separate on the core. So one is not wound over the top of the other at all. And I've tried to put as much space in between the two of them as possible. And we will see now how this performs.
Well, in a word, terrible. Just look at this. I mean, 19.1 to 1 SWR at 29.9 megahertz. So truly horrific. But it shouldn't surprise you, because we have wound these windings on totally separate parts of the core. So all that leakage inductance will be massive. So there's loads and loads of the inductance which is not contributing to the transformation process at all, and is just exhibiting this series inductance, which is why we're having such problems with it. So totally separate windings, no, that's never going to work very well for our purposes.
Now, my second attempt was to first of all wind the 20 turns of the red wire evenly over the core with a little gap at the bottom, and then to wind the 10 turns of the green wire over the top of it. And in actual fact, they're kind of partially interleaved, because the wires will kind of go into the gaps in between the primary 20 turns. But I didn't make any effort to spread them out evenly on the primary winding. So what I mean is, if you look at those green windings, you can probably just about see they stop about 2/3 of the way around the red windings. The green stops, because that's when I wound me 10 turns, and so I just kind of wound them without too much fuss until I wound me 10 turns. But it doesn't cover all of the primary windings. And I've got to be honest, I've built many transformers like this, particularly if you've got windings of a very big ratio difference. So if you've got just a few turns perhaps on the secondary and a lot of turns on the primary, you end up with just a few turns down one end. But anyway, so that's what I did here. Let's see how that performs.
Well, night and day, really. Much, much better than the separate windings. If we have a look at the SWR, you'll see that by the time we get to 29.9 megahertz, we're still 1.89 to 1 SWR, so that's not bad. That's not bad at all, you know, to be able to cover the whole HF band under 2 to 1 SWR. So that's a lot better. And actually, if you look at the impedance, you'll see the variation is a lot less as well. You could certainly make use of that, but can we do better?
And so now what I tried, using exactly the same pieces of wire and using the same ratio of 20 turns and 10 turns, I interleaved the winding. So that is, I wound my 20 turns in the red on there first. And then when it came to the greeny blue wire, because I've only got to wind 10 turns on the secondary, I basically put 1 turn of my green wire for every 2 turns of my red wire, and hopefully you can just about see that. So you've got 2 red turns, then a green one, 2 reds and a green, 2 reds and a green, as carefully as I could all the way around, so that actually both windings then, the primary and the secondary, are spread evenly over the core, with a bit of a gap at the bottom, of course. But also, both of them are very close to one another as well, and evenly spread with respect to one another as well. So that's what I'm calling the interleaved method. And let's have a little look how this particular one performed.
And again, in a word, this time a different word, brilliant. I mean, just take a look at this. The whole of the HF band at, well, almost, apart from the tiny bit where we've got a tiny bit of low frequency inefficiency just there, but basically the whole lot under 1.25 to 1 SWR. So, I mean, that is absolutely great. And you can see on the Smith chart how, I mean, the other ones had traces going right up here, showing the amount of inductive reactance that we were having to deal with. Very little reactance as well, which is marvellous. And even when you look here at the reactance, the figures are not high. I mean, there's a slope because we're going from 4 down here to 17, but it's not a massive amount. And look how flat this resistive part is looking as well, and look how flat the actual parallel impedance is looking. So absolutely great. So you could do this and you would be absolutely fine across the HF band. So the difference that it makes in interleaving those windings and making sure that not only are they tight on the core, but they're spaced evenly with respect to one another is quite remarkable. Well, there you go. But the question still remains, can we still do better? And I believe we can, because there is another kind of transformer which amazingly takes 2 of the things which are problematic to us in a conventional transformer, the leakage inductance and the interwinding capacitance, and uses these 2 things to our advantage in building what is, I think, an even better transformer, and we call it a transmission line transformer. But that is another subject for another video. So thank you very much for watching. If you've enjoyed this video, please remember to like and subscribe, and I will see you on the next video. Until then, look after yourself. Take care. 73. Bye-bye.